But then, of course, when you have your data, you maybe run a few different methods, you get slightly different results. In most cases, the top genes are the same regardless. It's still really hard to say what works best for my data. Then again, use your common sense and biology to judge. And a lot of different projects have tried to evaluate these methods, but the issue is that we don't really have any positive controls unless we use simulated data. But we can still compare how many genes do we get with this method, how much do they overlap. Sometimes it could also be nice that we do these two methods and these genes come up in both of these methods, so we trust them more. And then, of course, plot the data, look at it, and see if it makes sense. There is one paper that tried to do quite a lot of different methods. It's a while back, but I think most of these, several of these that are included in SciRat, and then also based on different normalizations before doing differential expression and so on. So it's quite an extensive comparison. And they tried then to rank all these methods on good, intermediate, and poor as a sum from all the different tests they did. And they actually find that edge R, when you normalize for detection rate, works quite well. Even and lemma trend also. So these are bulk methods, but they work quite well also for single cell data, also masked, either with TPM or counts per million. So there's quite a lot of these tests that gets good score, but also just t-test and Wilcoxon. You have the Wilcoxon here and the t-tests. They also give quite good results, even though the t-test makes the normal distribution assumption.
I just a small question here. What are these metrics on the bottom? So like Wilcoxon fails at complex design.
Oh,
so for the complex designs, because t-test and Wilcoxon, they only are paired comparisons. So if you need to regress mitochondria or add the batch effect to the model, that cannot be done in those tests.
I see.
That's what it is.
Because that's also something that's important to think about. For instance, now in the exercise, we integrated 6 samples. And then we want to do differential expression between cluster 1 and 2. We want to make sure that the differential expression is not driven by batch effects. So then you can add in factors, like for instance, the batch information, into some of these tests, but not all of them. So Wilcoxon is the default in SciRat, but maybe not the best when you also want to control for batches. And then also in these methods where they use bulk tools, and they say that it's really important to filter out the lowly expressed genes, the ones that are only detected in a few cells before running the test, especially if you start modeling dispersions and so on. And then also they look a bit at how these different methods overlap. So actually like MAST and this edge are lemma trend and Wilcoxon, they overlap quite a lot in what genes you get out from these tools, while some are clearly different. But then another trade-off is, of course, when you start having quite big data sets, Wilcoxon is a very fast test to run. Well, when you're starting to do a lot of modeling and so on, some of these tests will get a lot slower. But they're still quite well implemented to run fairly fast. But I would say MAST, for instance, takes about twice as long to run as the Wilcoxon. So that's probably one reason why it's the default method in Serath.